Welcome, everyone, to today's Explainer lecture. I am absolutely thrilled to have all of you joining me. Listen, my goal today is to provide you with a crystal clear, definitive framework for understanding the core foundations of artificial intelligence. We are going to cut right through the buzzwords and look at the actual architecture of how these systems operate. So go ahead and grab a seat, get your notes ready, and prepare for a highly focused academic deep dive into the fundamentals of AI and machine learning paradigms. Here is our syllabus for today's lecture. We'll be working our way through 1. The broad AI universe, 2. 3 categories of AI, 3. How machines actually learn, 4. The 5 learning types, 5. Understanding model families, and finally, number 6, connecting models and learning. Okay, let's dive right into this with section 1, the broad AI universe. I want to immediately clear up a very common misconception right out of the gate. Artificial intelligence is the broad, overarching field focused on building systems capable of tasks that normally require human intelligence. Notice that phrase, encompassing many different approaches. Machine learning is just one part of AI. It is absolutely not the whole thing. If you take away only one fundamental truth today, let it be this. AI is the entire universe, and machine learning is merely one galaxy within it. That brings us to section 2, 3 categories of AI. Let's explicitly anchor this contrast, because it's vital for understanding both the history and the future of our field. First, we have symbolic or rule-based AI. This is the older traditional form. Humans write explicit logic, and the machine follows it to the letter. Think of a classic chess algorithm calculating moves, or a basic chatbot where if the user types hi, the code explicitly tells it to respond hey. Then, on the flip side, we have the modern dominant approach, machine learning-based AI. Instead of strict human-written logic, the system looks at massive amounts of data and finds its own patterns. This is the engine behind complex, messy tasks like spam detection or speech recognition, where writing millions of manual rules literally just isn't possible. And sitting right smack in the middle, bridging the gap, is our third category, hybrid or neurosymbolic AI. It combines the strict logical reasoning rules of symbolic AI with the incredible pattern-finding power of machine learning. A great way to ground this concept is to think of a modern AI personal assistant. It uses machine learning, specifically neural networks, to understand the messy, complex audio of your voice, but then it switches over to logical reasoning layers to mathematically schedule your appointment in your calendar. That way, you can't blame the AI when you accidentally double book yourself for a Friday afternoon. It really is the best of both worlds. Now, what's really interesting about this next part is section 3, how machines actually learn. If you want to architect machine learning systems, you absolutely must separate the how from the what. I strongly emphasize this distinction to all my classes. First, consider learning types. This describes how the learning happens. It is entirely dependent on the kind of data you have available and the learning signal you provide. Then contrast that with model families. This describes what kind of algorithm, model, or let's call it the brain, you are using to process that data. So learning types on the method of study, model families are the brain actually doing the studying. Grasping this separation is absolutely critical for everything that follows in this lecture. Moving right along to section 4, the 5 learning types. We kick things off with the most common paradigm by far, supervised learning. We choose this method when our data already includes correct answers, which we call labels in the industry. I want you to lean on the analogy of a teacher supervising a student here. The teacher hands out a worksheet full of questions, but crucially also provides the answer key. The goal for the student, or the model, is to learn the underlying relationship between the input and that provided target answer. Why? So that later, when they're taking an exam without the answer key, they can accurately predict the right outcome. Let's walk through a highly intuitive example so you can see exactly what labeled data looks like in practice. Imagine a simplified data set for an email spam detector. For our input, we have the actual text of the email. For our label, we have the correct answer already provided by humans. So when the input is win a free iPhone, the label is spam. When the input is meeting at 3 p.m., the label is not spam. By feeding millions of these paired examples to the model, it learns that, hey, lots of exclamation points and the word free strongly correlate with the spam label. The label itself is the crucial learning signal here. But what happens when we literally don't have the answer key? Well, that brings us to unsupervised learning. Let's explicitly contrast these two. Supervised learning is all about predicting a provided correct answer. But unsupervised learning, that's about discovering hidden patterns, groups, or structure. There are no labels. Think of it like there are no backs of the flashcards for the model to check its work against.
The model simply observes the raw input data and tries to find some hidden structural logic entirely on its own. To show the practical, everyday value of finding these hidden structures, let's quickly detail 3 distinct business applications. First up, grouping customers. You don't know the exact categories in advance, but the model can cluster shoppers with similar buying habits together so marketing can target them better. Second, organizing images. You hand it a massive folder of completely unnamed files, and it groups the visually similar ones together. And third, finding unusual transaction behavior. Without ever being told what fraud looks like, the system simply flags a transaction that sits mathematically far away from the normal, everyday cluster.
Our third type is a whole different ballgame. Reinforcement learning is not about mimicking a static data set. It's about learning how to make decisions. The model learns by interacting with an active environment. It takes an action, and the environment pushes back, issuing either a reward or a penalty. Think of an AI learning to play chess by earning points for capturing pieces, a robot learning to walk by getting a reward for moving forward and a penalty for falling over, or even an algorithm figuring out what video to recommend you based on the reward of your continued clicks and watch time.
Now let's contrast the final 2 learning types, both of which deal with a very harsh reality in our field. Labeling data is incredibly expensive, time-consuming, and frankly, super boring for humans to do. First, semi-supervised learning. This uses just a tiny bit of labeled data, say 1,000 expertly diagnosed medical images, to guide the learning over a massive, unlabeled pile of maybe 100,000 images. And then we have self-supervised learning. Here, we have 0 human-provided labels. Instead, the system cleverly uses the data to create its own learning task. And this brilliantly illustrates how self-supervised learning actually works in practice. First, we take raw, unlabeled data right off the internet, like the sentence, "The cat is sleeping on the sofa." Second, the system purposefully hides a part of it, turning it into, "The cat is sleeping on the blank." Third, the system tries to predict that missing word. Because the original data contains the word sofa, the model can instantly check if its guess was correct. It creates its very own test without a human having to label a single thing. This exact same process is used to predict the next frame in a video or to rebuild a missing pixel block in an image.
All right, Section 5, Understanding Model Families.
We are now executing a major shift in the lecture. We are entirely done talking about the how. We are now moving over to the what. The architecture, the algorithms, the actual brains of the operation. I want you to have a complete taxonomic picture of traditional machine learning brains. Before the recent massive AI boom, these classic model families were the engines driving the entire industry. We've got linear models, decision trees which map out conditional logic, random forests which combine many trees together, support vector machines for complex classification, clustering algorithms like k-means, and dimensionality reduction techniques like PCA. These are all distinct mathematical brains that you can pull off the shelf to process your data.
So the crucial point is, and I want to heavily hammer home this massive industry misconception right now, deep learning is not a learning type. It is a model family. People constantly confuse deep learning with supervised or unsupervised learning. They are absolutely not in the same category. Deep learning is a what, it is not a how. Let's define what this brain actually is. Deep learning refers to a specific model family, neural networks that use many, many layers of artificial neurons to learn phenomenally complex patterns. It is incredibly effective for messy, unstructured data like images, audio, and human language. But remember our taxonomy. Because deep learning is just a brain, it can actually be trained using any of the 5 learning types we just discussed.
Which brings us to our final section, Section 6, Connecting Models and Learning.
This is the logical climax of today's explainer. We are now going to synthesize everything, combining the what, the model family, with the how, the learning type. Let's move to and see how this builds into actual real-world applications. Look at these exact combinations. This should really be your aha moment of complete structural understanding today. Example 1, an AI that perfectly recognizes cats and dogs. What is it? It's a deep learning model brain trained via the supervised learning method using labeled photos. Example 2, an AI organizing your phone's photo gallery. It is the exact same deep learning model brain, but this time trained via the unsupervised learning method to find hidden visual clusters. Example 3, a physical robot navigating a factory floor. Again, it's a deep learning model brain, but trained via reinforcement learning using environmental rewards and penalties. The brain stays the exact same. The method of teaching is what changes.
I want to conclude our explainer today by challenging you with this final, slightly provocative thought. As you step out of this lecture hall and eventually begin architecting your own systems, which question comes first? When you look at a brand new problem, do you first ask what brain you need to buy or how the system should learn based on the data you actually have on hand? Master that relationship, and you will have truly mastered the fundamentals of AI. Thank you all so much for your focus today, and I'll see you in the next session.